Alright, now that we've done a whole lot of approximation by hand and we've actually then executed a detailed analysis by hand, let's see how this plays out with a computer model. I'm using visual analysis here. I've turned off member self-weight. I have chosen a W30 by 191 beam, which actually is the US unit version, even though we're in the metric system. We have the steel material is steel ASTM A992 grade 50. That establishes our value of E. The W30 by 191 establishes the numerical value of I. The key thing in all of this is that EI and EI for each of the two beams are identical all the way throughout. And that was the basis of our analyses that we were doing before. And you might recall that the EI actually ended up dividing out of the system when we were executing the flexibility method. So that's critical. Now that will therefore mean that no matter what size beam or what material, as we look at these two, if we keep the EI the same all the way through, the reactions will be the same, all the statics will be the same. But what won't be the same, of course, is if we change E or I to a different member, different material here, the overall deflections we end up with will be, of course, different depending on what we end up selecting. Right? I've chosen this particular member because it made the design check such that it was adequate from a design standpoint, something that you would learn more about in the design class. You already know theoretically from your mechanics and materials class. Alright, so you do see a result down here. This is the deflected shape that we have in the system. We had talked about how in the previous part that we anticipated the longer span would be more flexible than the short span. And here we get, at least to a relative scale, a real sense of just what that might mean. Right now, this is grossly magnified in terms of real behavior. We would never end up designing a beam that would have this kind of flexibility, this kind of displacement in real terms. This is at least a factor of 100 larger than real truth, right? It's been expanded greatly. If I printed it to real scale, all you'd see is a big straight line. You wouldn't be able to see the actual deflections at all. So exaggerated for the purpose of being able to see it. We've got the smiley face going all the way through here, and then we have this region of frowny face, and so there's some sort of inflection point here, some inflection point there, and there's our support or our node, right, at the 20 meter mark. And so then we get a little bit of smiley face out here in the right. Notice that middle support is going to rotate in a counterclockwise fashion here, because although everything else is equal, this left span is much longer. 20 meters compared to 15, you think, well, that's not that much longer, but deflections are proportional to the length to the fourth power in this instance. So we are very sensitive to differences in those particular spans. From a stiffness standpoint, we'd actually be just only proportional directly to L over L in that particular situation, right? So let's take a look and dig into this just even a little bit more. Right, so this is the same thing, the deflected shape for the two spans. Note that our maximum is about 0.028 meters, right? So that's 28 millimeters, or about really 3 centimeters over here in the left. The maximum in the right span is about on the order of millimeters here. It's 0.3, and so wow, that's about 0.03, 3 centimeters. And this is about 3 millimeters. So there's a factor of 10 to 1 in these displacements, max displacements between the two. Right? Notice we do have this counterclockwise rotation at that middle support, right? And it actually, the beam hops up above its undeflected position a little bit here, so a little bit of minor hopping above, and then that's all frowny face curvature, and then it comes back around. Notice the frowny face curvature comes from the negative moment we have in that region, right? And so also note here we've got this max moment at the left. There's your 635. That's exactly what we have found before. There's your max negative moment, which was really the target that we were after. That's minus 812.5. We care so much about that because the compression flange is on the bottom, and that is a potential region where we may not have support for that compression flange. The deck would provide the top flange lateral support, and when you take the steel design class, you'll learn to call this associate this with lateral torsional buckling. You actually do get a little bit of support for the compression flange right at the support itself. So then what is of significance here for us is two things. One, the overall magnitude of this, and then this length that we have, this negative bending moment, is very important to us, because we don't have any or we have to be thinking about lateral support for the compression flange if it were steel. Right, now here's a little thing that I ought to go back and mention. I used steel here, right, and I just selected the size based upon that this was a steel member. But if you go back to the original photograph of the bridge, that was reinforced concrete. Actually, it wasn't reinforced, it was pre-stressed concrete. And so our deflections here are only representative, they're notional. They are not the actual deflections of the real bridge, just because I'm not using that actual cross-section size. But remember, again, the EIs cancel out, so it doesn't change our moment diagram, it doesn't change our shear diagram, it only changes the actual value of the deflections that we have up here. Right? So that was just a little brief aside that I just realized was kind of a contradiction in the analysis. Alright, so again, note, we got our max negative moments right at the support. Maximum positive moment is off-center in the span here, off-center in the span over there. Look at the numbers, 812 compared to 635 compared to 230. This negative moment is the largest moment anywhere in the beam. That's kind of a sort of interesting big thing, right? Okay, last thing before we charge off, note our reactions are given to us by our shear values. There's your 159.38 at the right. There's our 95.83 at the left, and that's at the right. And the total reaction is going to be the sum of the absolute values of those two shear values, and that's going to get us back to 444.8. Wow! So we were right. All that math that we did before was exactly right. All the moments values exactly right. We did it right. Yoo-hoo! Alright, so let's play a little game here and find out what happens when we start monkeying around with some basic things. Alright, so our total length of the entire system was 35 meters. We had a 20-meter segment and a 15-meter segment. Right? Now, if we were to put these two spans exactly then symmetric, then what the heck do we end up with on our reactions and all the other values? Right, so that would be A equal to 17.5, also B would be 17.5. And note the reaction is 437.5 in the middle, whereas our reaction for the 20 meter, that would be the A value, was 444.8. Right? So notice that when we start making the system asymmetric, that reaction then is going to go up in the middle. Right? So I'm sliding that R2 over to the right. I do slide it over just a little bit more. That reaction goes up a little bit more. I keep sliding it up. 502 goes up, over to 25, and it keeps going up. I keep sliding it over, and at 34, it's almost all the way over. Now, why am I playing this game? Well, take a look at the other reaction values. Right? As we slide this R2 to the right, not only does the middle reaction go up, but so also does the left reaction as I start moving that over. By the time I get all the way over to the right, it's nearly doubled. Right? That's kind of interesting. Right? But look what happens to the right-hand reaction as we move that middle support over. It's going down, 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 and actually at this critical location of 24.4 meters from the far left, then it actually becomes, I have it written as 0, it's actually 0.08 kilonewtons. It's really, really close to 0 here. That represents that as that thing moves over, that's a switch between this reaction being pushing up and keeping the beam from going down, to all of a sudden as we keep moving it over, this thing wants to kick up such that you have to hold down the beam out here at the far right. That's what's kind of going on here in this this little numerical game that I'm playing by moving that over. Right? So also notice what happens to the maximum negative moment. As this R2 goes over, that maximum negative moment is getting bigger and bigger and bigger and bigger and bigger and bigger. It starts to get really large as we start moving it over there. Right? Notice also here the maximum positive moment in the left span then also is increasing as we do this. But as we move this support over, the maximum positive moment in the right-hand span actually gets smaller to the point where actually you don't have a positive maximum moment at all. In fact, in that little turnover here, right at that location, you have nothing but negative moment as we slide this thing out to the far right. What's happening is this little system, little span here, is getting stiffer and stiffer and stiffer compared to this, the left one, and it changes its behavior as it gets a lot stiffer, from being this gull-wing moment diagram that we have here to now it'll all be just negative as this system is responding when you have moved that middle support over. Right? So there's a lot more you could peel out of this, and in other kinds of modeling techniques, that idea that the shorter span is going to be stiffer and how do we predict that stiffness would come out into in more directly. It's going to turn out to be real important to look at I over L of the span. So as the span gets shorter, it gets stiffer. As you make the I value larger, you'll make the whole thing stiffer as well. It's really EI over L that actually matters in that whole process, but geometrically you might just talk about that in terms of I over L, because usually the whole system has the same E, so that's not the big thing. Right? So that's partly what's going on. Now also note that as I move that R2 all the way out to here, it's not quite a simply supported beam. What you really have at that point, this becomes almost no rotation over here. You have a fixed end versus a pin end, and then the span length as for that whole thing has gotten close to L equal to 35. So that's why these values of these moments are getting so much larger, is because you have a lot longer unsupported span. Alright, so let's take a look and wrap this up here. You've got, for a two-span asymmetric span situation, uniform load, right? The inflection points move away from 0.1L for the middle spans of a many-span continuous beam, and towards, these are the outer spans, from 0.2L to 0.3L. Right? Even maybe longer than that in this case of the right-hand span. Right? The longer span has the larger maximum positive moment, and it's going to be actually greater than the square the ratio of the two spans. That's because, and what I'm talking about is, look at L1 compared to L2. Here that would be A compared to B, and square that, and you get the beginning sense of what the ratio of these maximum positive moments are going to be. This is so because, remember, it's a uniform load, so the second derivative of the moment is equal to the load intensity, and so if you integrate that twice, that's why you're getting this little business here. Right? The maximum negative moment occurs at the middle span or middle support. It's going to be larger than all the other moments, and you certainly see that in this table as we play around with those ratios. So the largest possible moment in the whole system is going to be that at that support. That was why in this whole problem we were focused on that negative moment to begin with. Right? If the second span is short enough relative to the longer span, the end reaction becomes a hold down force, and that short span experiences only the negative moment. That's this game we were playing with up here. And in general, that shorter span is the stiffer span, and in general, stiffer elements do tend to attack greater stress, although in this example, I'm not sure if you're going to see it in quite the same way. You have to know to look for that. Right? Alright, so what do I really want you to get out of all this, beyond just some of these things? When you're doing these after-action reflections, you need to be thinking a lot more than just simply, I got it done, check my answer at the back of the book, oh, I got it right, I'm done, ha-ha, great, good for me. Yes, good for you, I agree with that, for sure. But you need to be thinking much more deeply than that. This is not about trying to generate results. Right? We can generate results with a computer model. How do we know that this is a reasonable result? That's one of the things we got to start figuring out. The other part is, how do I know how to begin to decide what these kind of support members, what their sizes ought to be? How do I design these things? I need to be thinking about these bigger pictures of aspects of performance to be able to start to get that and to get to move forward beyond I'm just here to be a calculator monkey.